All right, so we are looking at section 2.2, polynomial functions of higher degree. They've got a little one right here somewhere, right there on the corner. Okay, so learning objectives, you do not need to write these down. Use transformations to sketch graphs of polynomial functions. I'd rather use this one. Can you not do that right now, please? Thank you. Use leading coefficient test to determine the end behavior of the graphs of polynomial functions. Find and use zeros of polynomial functions to help sketch graphs. And use the intermediate value theorem to help locate zeros of polynomial functions. All right, so just to make sure we're understanding what continuous means. The graphs of polynomial functions are going to be continuous. That means no holes, no gaps, no breaks. So they're nice, rounded, smooth kind of curves, no sharp turns. All right. Consider polynomial functions that have only one term, like f of x equaling 3x to the fifth. If you graph these on your Inspire, we graph these on the Inspire, like x squared and x to the fourth, how are these going to be similar? How are these going to be different? Go ahead and grab those calculators, please. On one graphs page, I want to see you graph both of these so that you can compare. All right, so they are, okay, so they're both this kind of U-type shape, but what would we say, the parabola and the degree 4 is that kind of wider on the outside or steeper on the outside? Steeper on the outside. And is the degree 4 rounder on the bottom or flatter on the bottom? Flatter. All right, so that gives you an idea of how these are comparing. All right, and notice, same thing kind of holds with x to the third and x to the fifth. If you try those, go ahead and try those on another graphs page. All right, so the higher the power, the flatter the graph near the origin. All right.
I just did it. It looks like 12 marks.
Okay, so, excuse me. So if you're going to describe the transformation and sketch the graph of opposite of x plus 5 to the fourth, you know that the parent function that you just saw on your calculator looks something like this, kind of wider, flatter, like this, right? Okay, but if we're going to do x plus 5 quantity to the fourth, forget about the negative for right now. What effect does that have on your graph? Shifts to the left 5. So picture this shifting to the left 5. And then what about the negative out in front? All right, reflects it over the x. So it's going to end up looking something like this, right? Are we okay with this? All right. So just without typing this into your calculator, describe the transformation for this graph. We got 1/4 x minus 3 quantity to the fourth plus 1. Give me one thing about this here. Oh, snap, that's not you. Justin. All right. Shift right 3. What else about this, Jack? Shift 1 up. What else?
It's a horizontal vertical shrink.
It's vertical.
No, it's horizontal.
I don't know, you tell me.
Vertical shrink.
Vertical?
Yeah.
How do we decide?
Because it's one of the...
If it's out in front of the whole thing, it's going to be vertical. So it is vertical compression or a vertical shrink
Of what?
of 1/4. If it had been 1/4 x raised to the 4,
Then it'd be horizontal.
that would be a horizontal what?
Horizontal stretch.
Stretch of
Four.
4. All right, everybody okay with this? Reminding you of things that we learned back in chapter 1. Okay, at this point, we are going to, I know what I want to.
That was a vertical.
This one was a vertical compression or vertical shrink of 1/4, but this one, if it had been 1/4 in parentheses with the X, then it would have been a horizontal stretch. All right, so in your book, there is a little activity that I would like you to do on page 141, excuse me, page 141, and you are going to need your graphing calculator, so if you would take out that. I would like you to do where it says exploration. It says for each function, identify the degree of the function and whether the degree of the function is even or odd. Identify the leading coefficient and whether the leading coefficient is positive or negative. Use a graphing utility to graph each function. Describe the relationship between the degree and the sign of the leading coefficient of the function and the right hand and left hand behavior of the graph of the function. So let's do the first one together. So we're doing this letter A. So it's f of x equaling x cubed minus 2x squared minus x plus 1. So what is the degree of this function? Okay. All right, so the degree is 3, right, from right here. And what about the leading coefficient? 1. So I want you to say the leading coefficient is positive, and the degree, instead of writing 3, I want you to say the degree is odd. All right, because we're trying to make a generalization about the graphs of all odd degrees with leading coefficients that are positive, or all odd degree polynomial functions with leading coefficient negative, or whatever it happens to be. So now you're going to type this into your calculator on a new graphs page. And I'm hoping you're going to save this document as like 2.2 homework or something like that, or 2.2 notes. All right? So you're typing this in? No, for right now, all we're interested in is, does it start low and end low? Does it start high and end high? In other words, does this graph, does this graph, God bless you, does this graph look something like this? Or does it look something like this? What does it look like?
It looks like a stupid.
All right, but tell me, does it start low and end low? Does it start? All right. So starts low and ends high. So something like this?
No, I mean.
No, it goes low and below. Okay.
But I don't care about the intermediate parts. I just want to know, does it start low and does it end high? Okay, so what I want you to do is write that down. So for letter A, this is all the information we have about letter A, and I want you to write that it starts low and it ends high. Does everyone understand what you're doing? All right. Would you please do B through G now? But the only thing is, I want you to change. Can we change letter G so that it's a negative x squared plus 3x plus 2? Because I don't think they have any even degrees with leading coefficient negative. So can we change G to a negative x squared plus 3x plus 2? Thank you. And I'm pausing this video while people are doing this activity. Okay, so just to sum up, we said that if the degree is odd and the leading coefficient is positive, then it's going to start low and end high. But if the degree is odd and leading coefficient is negative, it starts high, ends low, which means in general, for an odd degree, they're going to start and end in opposite places. All right, if we are talking about even degree polynomials, if the leading coefficient is positive, they're going to start high and end high. And if the leading coefficient is going to start low and it's going to end low. So what generalization could you make about all even degree polynomials? All right, they're going to start and end. They're going to start and end the same way, right? Same direction. All right, what about, can you make any generalization about all the leading coefficient positives? What's a generalization we could make about those? All right, they always end high. So, you know, if you're a positive person, for example, things are going to work out okay for you. End high. All right, but if you're a negative person, then things end. All right, so ends low. Would you agree with that? Not necessarily the psychological thing, but the summary. All right. Okay, so the only thing I would say is to just, I'm going to come back to that in just a minute. If we're talking about polynomials in general form then, if the degree is a degree 1, that would be like f of x equaling ax plus b, right, where a is your leading coefficient. You know what that graph looks like. It's a line, and it's going to be having a positive slope, right? But if a is negative, all right, it's still odd degree, starting and ending in opposite places. Positive leading coefficient, it ends high. Negative leading coefficient, it ends low. Agreed? What about a degree 2 polynomial? That would be, let me squeeze this up here, ax squared plus bx plus c. So that, what shape?
Starts high, ends high.
All right, so it's a parabola, and it's going to start high and end high if the leading coefficient is positive. Starts low, ends low. You get the idea? Yeah. So for degree 3, that's going to be starting low, ending high here, starting high, ending low here. Agreed? Sure. Degree 4 is going to start high, end high, but it may have, you know, an additional, you know, squiggle to it, so it might look something like this.
Why?
Potentially. The extra x cubed, x squared, x to the first, whatever, that kind of gives it more flavor, so it might have more of a twist to it.
I like that.
All right. Okay, so that would be the type of shape you might see for a degree 4. Does this make sense? Every time you increase the degree, you are adding one more potential twist to the graph. So it could look something like this. You get the idea? Okay, so the leading coefficient test is basically what we were looking at here, except the leading coefficient test, come on, you are honor students, so we're not going to be just saying starts low, ends high, or whatever. We're going to use a little bit more sophisticated mathematical language. All right, so if we're going to redo this with more sophisticated mathematical language, pardon me? So if this one, we said that this starts low, ends high, right? So we're going to say, for starting low, we're going to say as x approaches negative infinity. That means where's it starting, right? That means the further you go to the left on your graph, then f of x goes where? All right, I'm just kind of taking my shortcuts. I know you guys can't do this, but I'm going to do this. Don't be like that. Just a moment. Give me a second.
I'd like to take this time to.
This is
The coolest thing I've ever seen.
this is an infinite cloner. I just cloned that. Let me make this a little bit bigger so it fits a little better.
Professor, you're a scientist? I didn't know that.
All right, anywho. Okay, so what do we say? If as x goes to negative infinity, that means we're heading to the left. F of x is going down, so we're going to say it's f of x approaching negative infinity. We're going to say that instead of it starts low. Does that make sense?
Yeah.
And then as x approaches positive infinity means the further you go to the, that's supposed to say to the right, it ends, so we're going to say positive infinity because it ends high. Does that make sense?
Yes.
Can you fill in the rest of my blanks here with positive infinity or negative infinity in the appropriate place?
I don't think so.
What?
Is that a negative 9?
That's supposed to be negative infinity.
What's that night?
I wrote 90.
Wait, oh,
That's what I got confused.
my bad. Is that better?
You draw your infinity.
So as x approaches negative infinity for degree odd leading coefficient negative, that means we're starting high. So f of x is approaching what? The further and further we go to the left, it's going where? Positive infinity. And this one's going to be negative infinity because it ends low. Everybody agree? What about this one? As x approaches negative infinity, again, that means the further we go to the left, what's happening with the function? Positive infinity because it's starting high and it ends high, so this is also going to be positive infinity. All right, what about this one? They're both going to be, the further we go to the left, it's heading down, right? Starts low, so it's negative infinity. The further we go to the right, again, negative infinity. Are we okay with this? All right, that is the leading coefficient test. So let's zip along to... I don't think we need more practice with that then. I think you're okay with this. So let's go on to the zeros of a polynomial function. A function f of degree n has at most n real zeros and n minus 1 turning points. All right. What are turning points? Turning points are also called relative minima or relative maxima. They are points where the graph changes from increasing to decreasing and vice versa. So let's take a look at, for example, a degree 3 leading coefficient positive. You know that that starts low, ends high, so something like this. Agreed? Yeah. A function of degree 3, I'm choosing n to be 3 here, right? A degree 3 has at most 3 real zeros in this case. So that means if this graph was like this, do you see how it would have 3 real zeros? Yeah. One here, one here, one here. Agreed? But if, it doesn't have to have 3 because this could have been up here, right? And so then how many zeros would I have?
1.
1. What if I move it up here? How many zeros would it have?
1.
Still 1, right? This keeps going, right? What if I draw it like this? How many zeros would it have?
Probably
2 real. You get the idea? We're talking about 2 real zeros, okay? Because what we're going to learn in this chapter, and I'm giving you a little sneak peek at some other sections, is if it's a degree 3, it's guaranteed to have 3 zeros. I'm going to say that again. If it's degree 3, it's guaranteed to have 3 zeros, but they won't always be real, right? You might have 1 real and 2 imaginary, right? Or you might have 2 real, but one of the real, whoops, where's my 2 real? You get the idea. If I have 2 real like this one actually is going to count twice because it's bouncing, and we're going to talk about that today. All right. All right. So what about the turning points? If it's degree 3, it's going to have 3 minus 1 or 2 turning points at most. So in this case, where are the turning points? Well, here's a turning point because it's going from going up to going down, right? It's changing direction. And here's another turning point, it's going down to going up. So a degree 3 has at most 2 turning points. Does that make sense? All right, so finding zeros of a polynomial function, one of the most important topics in algebra. You've been solving solving equations and finding zeros, I think, for a long time. All right, so real zeros of polynomial functions. If f is a polynomial function, if f is a polynomial function and a is a real number, then the following statements are all equivalent. Here's the first statement. X equals a is a zero of function f. So let's get a little example so we are all on the same page with this. Let's say our function is x squared minus 9. I think I'm out. I got it. Yes, you may. Okay, so what would be a zero of this function? 3. All right, so we can say x equals 3 is a zero of function f. Everybody agree? That statement is equivalent to this statement that x equals 3 in this case is a solution of the polynomial equation f of x equals 0. So x equals 3 is a solution, I'm abbreviating, of x squared minus 9 equals 0. All right, so we can say it's a 0 of a function, we can say it's a solution of the equation, and that is equivalent to saying that x minus a, in this case x minus 3, is a factor of the polynomial function. So we can say that x minus 3 is a factor of our function f of x equaling x squared minus 9, right? X minus 3 is going to be a factor of that. And same thing is equivalent to saying a comma 0 is an x-intercept of the graph. Well, that's saying 3 comma 0 is an x-intercept of the graph of function f. Are we okay with this? These 4 are interchangeable. They all mean very similar related things. Okay? And we don't need to do that because we just did this example. All right, are we okay with this? So I'm not doing that. Okay, so let's talk about this example. Find all the real zeros of f of x equaling x. I think that's supposed to be an x. This should be an x squared, I think. So let's do that. I hope. Yeah, all right, so find all the real zeros of x cubed minus 12x squared plus 36x, then determine the number of turning points. So how could we find the zeros? What should we do? Okay, so you want to set the function equal to 0, so we're going to solve x cubed minus 12x squared plus 36x equals 0, because to find a 0 of a function, you set the whole function equal to 0. You're trying to find the value or values that make the function equal to 0. Paul? All right, we can factor out an x. So x squared minus 12x plus 36. All right, we can do product sum on this, or if we recognize it, we can just, so x times x minus 6 times x minus 6. All right. So what are the zeros? We set each of these equal to 0, correct? All right, so the zeros would be 0, 6, and 6. Agreed? All right, notice to degree 3, how many zeros does it have? 3. They happen to all be real, but one of them is repeated. But if you count repeated ones, there's going to be 3. Does that make sense? All right, so let's talk about the repeated 0 thing. Repeated zeros. Oh, I know. Before I wanted to do this, go back. Can you please graph this function on your calculators? Where should we see x-intercepts for this graph, now that we found the zeros? 0 and 6. Go ahead and graph it on your calculator. I'm going to use some clues here. I know it's a degree 3. Leading coefficient is positive, so I know it starts where, ends where? Starts high, ends high, starts low. Starts low, ends high. So I know that the general shape I want looks like this, right? Agreed? That's the general shape. But where are the zeros? 0 and 6, right? So I want to get this general shape going through these points. But what's different about these two zeros?
It's a parabola on 6.
Well, I want... So it's crossing through here, and what's it doing here? Kind of bouncing off here. So does the graph look something like this?
Yeah.
All right, so why is it bouncing here and crossing here? That's what we're going to talk about right now. Repeated zeros. So a factor x minus a raised to the k power, where k is greater than 1, yields a repeated 0 of multiplicity k. So in this case, we have an x minus 6 as a factor, and that happens twice, right? So it's x minus 6 raised to the second. So we would say that 6 is a 0 with multiplicity 2, right? Agreed? Okay, if k is odd, then the graph crosses the x-axis at x equals a. So in this case, we could have written this polynomial function as x minus 0 to the first and x minus 6 to the second. Would you agree? So then the 0, is a 0 of the function with multiplicity 1, but 6 has a multiplicity 2, right? So since k is odd for the 0, then the graph crosses the x-axis at that point. And if k is even, then the graph bounces off the x-axis at x equals a. So it touches the x-axis but does not cross it. Does that make sense? So if I give you an example, like f of x equaling x times x minus 2 squared times x minus 4 to the third. Without typing this into your calculator, first of all, can you tell me what degree this would be?
Third. Oh, it's the first.
Who said 6? I heard it over here. No one's admitting it. Who said 6? Patrick. Why do you say 6?
Because it's the first leading one of x minus 2 squared, x squared.
If I was to multiply this out, sure.
And then we do the third one is the x cubed.
Okay.
And then there's x. So you like multiply them all together, and when you multiply, you add x.
All right, so if we multiplied this out, x minus 2 times x minus 2, that would be degree 2. If we multiplied this all out, we'd have a degree 3. And we still have to multiply by 1. So we can really just add these exponents. So this is going to be a degree 6. So it's an even degree. Remember what we talked about, even degrees, right? And then what about the leading coefficient? Yeah, it's just 1. I didn't make this one very interesting. So leading coefficient is positive, right? And then what about the zeros of the function?
It was the 0, 2, and 4.
0, 2, and 4. Do people agree?
Wait, how? At the beginning of it.
Oh, no.
Well, you guys set these equal to 0, right? Okay, but if it's a degree 6, how many zeros should we be?
There should be 6.
Should be
but
6.
there's multiple.
All right, so there's multiple zeros. So I want to say 0, 2, 2.
And then 4, 4, 4.
Does that make sense? Okay, so before, without graphing, is it going to cross or bounce at 0?
It's going to
Cross at 0. Is it going to cross or bounce? And is it going to cross or bounce here?
Well, it's gonna cross at 4 and then bounce at 4.
It's odd, so it's going to cross. Does this make sense? Because really, think of this x minus 2 quantity squared. I could have written it as x minus 2 times x minus 2. And if I set this one equal to 0 and this one equals 0, I get a 2. Does that make sense? So if I was going to graph this one, leading coefficient positive, I know that the general shape is going to start high and end high. Agreed? Right? And I know that my zeros are going to be at 0, 2, and at 4. Agreed? My graph is sloppy. But I know it's going to start high, and it's going to cross through here. So something like this, you with me? It's going to bounce at 2, right? And not cross, and then it's going to, does that make sense? Okay? All right, so that's just a rough sketch of what we can do just by looking at the zeros and the degree and using the leading coefficient test.
So, like, how do you know if it would cross or bounce, like, based on that?
So if the exponent here is even, it's going to bounce. And that's because we've got even number, right? We can see the even number of zeros. And if the exponent here is odd, that 0 shows up an odd number of times it's going to cross. Okay. Okay, so let's try this example. If we have this function, let's see, Brendan, what's the degree of this function?
Really?
Brendan, work with me. What's the degree? Why are you guys all holding up your fingers for him? He can do this. He can do this. It's this high. It's the highest power you see in any of the terms. So it's degree 3. All right. Brendan, what's the leading coefficient? All right. Does anyone have to hold up fingers for you on that one? All right. All right. And to find the zeros, we're going to need to factor. So if we factor out what? 2x squared. And then what's going to be left?
X minus 3.
Everybody agree?
Equals 0 and 3.
So what are the zeros? I'm going to set this equal to 0. I'm going to set this equal to 0.
It equals 0 and 3.
0, 0 and 3.
0, 0, and 3. Everybody agree? Okay? So that means that those are my zeros. And then, so then if I'm going to graph this, general shape, does it start high, end high, start low, end low?
Start low and high.
Start low and high. Do people agree?
Start low and
All right, and it's going to go through 0 and 3, right? So what is my sketch going to cross and bounce like this? Do people agree?
No, it's the other way. It's the other way.
No, it's cross on the 3 and bounce on the 0.
So bounce on the 0
Yep.
bounce.
and then cross. So something like this. Does that make sense? All right.
So should we memorize that table
I would. I would.
along with the unit circle?
Yeah, along with that unit circle. Yeah, no time like the present. Okay.
I'm not trying to.
All right. How about this one? This will be our last example. So f of x equaling negative 1/4 x to the 4th, 3/2 x cubed minus 9/4 x squared.
Degree 4.
Degree 4.
Leading coefficient is negative.
Degree is even. It's degree 4. And leading coefficient is
Negative.
negative. So does it start high, end high, start low, end low? What's it doing?
Starts low and slow.
Starts low, ends low. So the general shape is going to look like this. I'll just write general shape, right? Start low, end low. Didn't you tell me?
Yeah, that little curve thing is. Yeah, it is.
Well, it may have that extra. I'm mostly talking about that it's starting low, ending low kind of thing. All right, now what about finding the zeros? Can we factor something out here?
Yeah.
What can we factor out?
1/4 x.
1/4? How about a negative 1/4? Negative 1/4 x squared? And what's going to be left?
X squared plus this denominator so bad.
It's okay.
Plus 2
That's no problem for you.
There's other two things.
So negative 1/4 times what gives me 3/2. I'll call this W. How would you solve for W?
multiply by 4. So
All right, multiply both sides by a negative 4.
6.
So what's it going to be?
6.
Negative 6. So I want a minus 6x, and then what? I want negative 1/4. What's this one going to be? Do we need to do this, or we can do this?
Multiply by 10. 10 minus 9.
It's going to be 9. So plus 9, minus 9, plus 9. All right, so can you factor this?
Yeah, my backpack doesn't have to.
Okay, and then that was.
All right, so I've got negative 1/4 x squared times x minus 3 squared,
So
right?
0 and then
So what are the zeros?
0.
So it's gonna be 0, 0, 3, 3.
All right, would you please quickly, got 2 minutes, I want to see you, without doing a calculator, I want to see your best sketch right now on paper. I'm coming to see. And I am stopping the video.
Of this one?
So the final graph should look like this for this one, and that stops this video.